welcome everyone. So we're going to move on to fluids. I've taken a slightly different approach to my presentation, knowing that so many people at universities are not up to date with them, not just the last release, but maybe the last 5 or 6 releases. I'm going to look at a slightly wider background and based on some of the things we see in support. So one of the most important things to discuss is meshing. CFD only starts once you've got a good quality mesh, and Ansys have come up with this really powerful, what they've called Mosaic meshing technology, which allows us to link together all sorts of different meshes. So we all know we need our high quality prisms at the wall if we're going to capture boundary layers and heat transfer. But what we can do now is have a hex core mesh, and hexes are the most efficient that we can mesh with. And then Mosaic allows us to join those via polyhedra. So previous hex core meshes join these with TETs, and they're known to be not very robust. This technology allows us to join them in a much better way. So not only is the meshing technology improved, but we're seeing some easier ways of accessing the technology that we've got. And the way that's being done is that Fluent Meshing now has a couple of templates. So one of those is called watertight, which is fairly self-explanatory. It means you can get a nice clean CAD model, either for an internal or an external flow, and you can just go ahead and mesh that. And there's a guided workflow that takes you through that, allows you to put on mesh controls. It even allows you to extrude regions of mesh to put exit pipes and that on when you've done it. So that's one class of meshing. The other class is when you've got something really complex. Let's take this Jeep down the bottom here. If you bring that in from CAD, it will have so much detail that if you try and mesh every aspect of it, you'll go crazy. And probably because the CAD was made for manufacturing and that, there'll be holes, there'll be gaps, there'll be some slight overlaps. So what we can do now is use what's called fault-tolerant meshing, where we can wrap objects. So think of it as wrapping a piece of cling film around the object you want, and then choosing what resolution you resolve that wrap. So if you keep going down and down in resolution, you get back to the original geometry. But it allows you to wrap over small holes, gaps, slits, etc. And so, particularly for those doing external aerodynamics, it can be a really good way of cleaning up a CAD geometry and getting a nice mesh on it. Now, coming at the very latest release, just come out, is the ability to bring multi-zone meshing in here. So these are hex core, but suppose we want to actually have some sweat mesh, and that's quite common if you've got thin components of that. You can now designate regions that you apply this multi-zone mesh on, which is essentially a sweat mesh. So there's now a very powerful set of tools, and if you're doing CFD, you really should turn to Fluent Meshing as your meshing tool now. Another technology that's been gradually introduced over the last few years is overset meshing. And you can now set up overset meshing in that fault-tolerant workflow. So what does overset meshing mean? What it means is if we want to model this runabout boat here with a propeller and that on, and we want great flexibility of how we change the direction and that, we can now do that by putting a high quality mesh around that object, the whole impeller and drive train here. And then we can overlay that on a background mesh, and the code will work out where these join, and it will have separate solutions being solved inside this mesh and the background mesh and linking them together. And there's all sorts of nice options to make sure that you get really accurate transfer between the two. Academics think of mesh refinement as start off with a mesh size of 2, then make it 1, then make it a half, and very quickly you realize that that's not something you can ever do out in industry. What you're actually going to do is put your mesh where you need it. And there's huge amounts of work going on to do mesh adaption. And not only for steady flows, but as you can see, for highly transient flows. And in the last release, we introduced the first release of what's called Hessian adaption, where you're actually adapting to almost like the error term, because you're looking at second derivatives and trying to put mesh where you've got large second derivative terms. So you can see that this is a much, much more efficient way of actually getting fine mesh where you need it. And the fact that the mesh follows the solution and it can be added and subtracted where it's no longer needed. And we've seen particularly large benefits for free surfaces, compressible flow, and combustion. Almost everybody needs to use turbulence. And if you were to ask 100 academics what their favorite RANS model was, you'd get 100 different answers. So what we've done in the software is to come up with a generalized model based on the K omega formulation, but where constants in it are separated out so they affect a particular type of physics. So that you can, for example, change separation behavior or spreading rates or transfer near walls or jet flows. And you can actually change these not only globally, but also locally within a flow. And there's now lots of work going on to optimize those choices using the optimization tools. And with this model, you can change one constant and essentially go from K epsilon to SST, and you'll see that the GEKO versions give identical results, but then you can go on to tune your model. Why do we do this? Well, we do this because we can't always afford to run scale resolving simulations. And if we do need scale resolving simulations, though, we have this ability now to run a model called SBES, stress blended eddy simulation. What this allows us to do is in regions where the mesh refinement is adequate, it will switch to a large eddy simulation. And that's really important because a large eddy is seen as an important contributor to good quality turbulence modeling, but it's often abused and applied at walls and things where the RANS model is actually better. So here now we can make use of the optimum model, and it's great for combustion, acoustics, vibrations, that type of problem. I'm just going to chuck up a couple of slides on hypersonics. We know about rocket competitions and there's a lot of space work going on in the news now. If you're working in hypersonics, Ansys has invested massively in new technology and solver capabilities, ranging from 2 temperature models, so we can get much better dissociation, very robust numerics, and oops, okay, I haven't got a movie, but this is ablation. Combustion, always a big area. Combining those high quality turbulence models with now flamelet generated manifolds or very good finite rate chemistry. And particular, the focus of this slide is on hydrogen. Lots of validation going on, flashback simulations. So if you're in the combustion area, there's lots going on. VOF to DPM, this allows us to take a continuous fluid with volume of fluid, have it break up a jet, and then at a certain point where these filaments are sufficiently spherical, turn them to a discrete particle model. And this can go all the way. These droplets can actually form a puddle, go to a film, and then go back to VOF if we want. And what you'll see here is this is a way of saying that lots and lots of work has gone into free surface flows and into particle modeling. And this cannot be done here without the combination of mesh adaption and the SBES model to give you really good turbulence resolution. Multiphase could show you lots of different things, but I think one of the key things to show is in these videos that there are now all sorts of regime maps we can do where we've got air entrained going up into a continuous phase. So we've got bubbles, we've got an oil where the behavior is quite different, and then we've got a non-Newtonian catch-up filling up. And what continues to happen within Ansys is improvements to the technology and the physics models that go into this. A really exciting development. It's a beta feature at the moment, but something that you may like to try. This is a solver that runs entirely on a GPU, giving massive speed up. And at the moment, it's got quite significant capabilities already. Transient, scale resolving, or RANs, a moving reference frame, porous media. So you can see that this first release is really focused around aerodynamics. So give it a try. And if you're interested, contact us. Several of my colleagues are really into this. And then my final slide is to just mention what's happening at Ansys, that we know that Python is becoming the dominant programming language and certainly taught at most universities. Interfacing with the software, Ansys is opening up its software to Python interaction, and those are the mechanical, the Fluent package, plus they've also got their own graphics package and that now. That very much the first release of PyFluent, but this is the type of syntax you're going to see to set up a problem and create graphics. You can go to the GitHub and download it and have a play, and I'm sure we'll be presenting more on this in the future. So a bit of a summary: rapid changes in technology and physical models. Very expandable. Fluent now has expressions as well as user-defined functions. We can do a lot of this customizing now set up through Python. Significant learning resources, as my colleague Joe pointed out. And don't forget, I've skipped over a vast amount of software I didn't have time for here. So whatever you're doing in the fluid space, if you think that you need some software to help, do contact our support line.